welcome. I am Nigella Hilgarth. I'm the Executive Director of the Birch Aquarium at Scripps Institution of Oceanography, UC San Diego, and it is my pleasure to welcome you to the latest Perspectives series in ocean science, the latest Jeffrey B. Graham Perspectives Lecture. And tonight it is my great pleasure to introduce the speaker, Dr. Richard Somerville. Richard Somerville is a distinguished Professor Emeritus here at Scripps Institution of Oceanography after a very distinguished career at Scripps and elsewhere. And he's a theoretical meteorologist, and he's an expert on computer simulations of the atmosphere. He received a PhD in meteorology from New York University in 1966, and he has been a professor at Scripps since 1979. I have to confess that I was practicing this, and I'm dyslexic, and I kept saying that he had got his PhD in 1996, but 66 is correct. And so his research is on the physics of clouds and their role in the climate system, and his interests include all aspects of climate, including climate science outreach and the interface between science and public policy. And he comments frequently on climate and environmental issues for the media. He's received so many awards, written so many distinguished academic papers, books, book chapters, and I don't want to spend the whole evening doing that, but I do want to mention that he was the leading author, or one of the coordinating lead authors for the 2007 fourth assessment report of the Intergovernmental Panel on Climate Change, the IPCC report. And I think most of you know that the IPCC report shared a Nobel Peace Prize with Al Gore. So I think he's something like 1/15 the Nobel Peace Prize winner. So I think that's highly distinguished. But I think the most important thing you need to know about Richard Somerville is that he is not only an extremely distinguished climate scientist, but he's one of those rare individuals that is also extraordinarily good at communicating to the public. And so he is able to paint an amazingly accurate and important picture of what climate change is doing to the planet and why we should care and why we should do something about it. So it is a pleasure and an honor this evening to introduce Richard Somerville to you. Thank you. Before I forget, Richard has been signing his book, and he's very kindly offered to sign after the lecture too. So this is a wonderful summary of his work and about climate change.
So thank you, Nigella Hilgarth. Thank all of you for coming, and indeed it will sign books afterward. Thanks also to those of you who bought the book. I'm happy to tell you I don't have any financial stake in it. I waived royalties. I just want a lot of people to enjoy this book, which is written for the general reader and doesn't have any nasty charts and graphs and mathematics in it. So I'll brag about the book later on, but it's my child and I want you to enjoy it. I've put my website address up on this slide, and within reason I'm happy to answer questions. If you go to richardsomerville.com, you'll find my email address, and you have some questions, then within reason I'll try to answer them or put you in touch with people who can answer them, because we're really going to have time just to hit a few highlights. And I want to start out by talking in a rather personal vein about the parallels between climate science and medical science. You know, we really are planetary physicians. And I think, like the findings of medical science, it'll turn out, I think, for many people, that to discover that climate science, while it's imperfect, while there are things we don't know, it's still useful. And that's true of medical science too. When you go to your annual checkup and your physician tells you to shape up and lose weight and stop smoking, you don't attack her as a radical alarmist, and you don't complain that she can't predict the date of your heart attack. And so we understand that there are limitations to climate science and limitations to medical science, but that they're both useful. And that's true. I think the parallels are much deeper than that. We talk about global warming. It's a kind of parallel to a fever, and you know, we don't limit your discussion of your health to fever. It's a symptom. And so when we talk about the planet warming a few degrees in coming decades, that's a symptom for a whole line of climate changes, everything from heat waves to disruptions in water supply to melting ice and rising sea level and stronger hurricanes and changing rainfall patterns. The global warming number itself may seem small, a degree or 2 or 3, but like a fever, a small number when it's applied to the whole planet is a symptom of serious consequences. Recently, I think the world has come to accept the reality and seriousness of human-caused climate change, and I'm optimistic about that. I think that's a positive change. It's something that happened a long time ago in medicine. You know, when journalists cover a medical discovery, they don't act suspicious of reporters, and they don't insist on hearing from the opposing side, and they don't frame the issue in terms of a dispute or a debate. And journalists don't seem to seek out medical contrarians for balance. And I think that's changing too, and that the reality of mainstream climate science is coming to be widely accepted. And often it takes a long time. Think how long it took between the discoveries, the initial discoveries connecting smoking and disease in the 1930s and the highly publicized lawsuits in this country in the 1990s. There are many other parallels. You know, quitting smoking is like quitting using fossil fuels. It's hard to do. It's painful. And you have to do it right up front, whereas the benefits of doing it, in both cases, tend to come much later. I don't want to belabor this, but I want to get you thinking along these lines to put what I have to say in context. Medical decisions often involve substantial risk. Elective surgery is often in that category. It costs money and it's not without risk, but declining it is also not free of cost and not free of risk. And I think these kinds of things are true when we come to talk about the policy options that might be taken to cope with climate change. I want to close this little medical sub-talk by reminding you what Roger Revelle said famously in the 1950s when he was director of Scripps and UCSD didn't yet exist. He famously wrote in a paper with Hans Suess that humanity was doing a one-time inadvertent, unrepeatable experiment, putting back into the atmosphere a substantial chunk of the carbon that had been stored in the ground for a long time, and that we'd learned something from watching the consequences of that experiment. But I think for many people, that was visionary at the time. It's a truism today. But many people don't yet realize, I think, that we are now, we the planet, are doing another inadvertent and irreproducible experiment. We're going to find out whether people are going to take climate change seriously enough, rather than just procrastinating until the predictions that I'm about to tell you about come true. So as in the case of many medical decisions, if you want to think of this as a case of planetary physicians prescribing for the planet, ultimately the outcome is in the hands of the patient. That's a prologue to a personal story I have to tell you. I switched doctors this year, and my old one retired. I got a new physician. I went to see the new physician, and he said something to me and did something that no previous doctor had ever done. He said, "Sit down, I want to tell you how I feel about practicing medicine." He said, "You need to know 3 things. 1, I'm competent, I know what I'm doing. And 2, I have some integrity. When I don't know, I'll tell you. I'll level with you. And 3, I'll advise you, I'll diagnose, I'll recommend, and we'll discuss, but in the end, you, the patient, are going to make the decisions." And I was blown away by that because first, no other doctor had ever said that to me. It seemed strikingly honest. I liked it. And second, I thought the parallels with climate science were extraordinary. Because the organization that Nigella Hilgarth mentioned, the Intergovernmental Panel on Climate Change, which has taken up half my time for the last 3 years and the time of many other scientists here at Scripps and worldwide, is very much in the mode of trying to be a wise physician. Its job is to assess climate science, not to do research, not to make recommendations on what policy to follow, but simply to look at the body of published, peer-reviewed technical literature, the place where scientists publish their research results, and assess it, and make a judgment that's relevant to policymakers without being prescriptive of policy about what we know and what we don't know, and how sure we are. And the IPCC, this organization that shared the Nobel Prize with Al Gore in 2007, is careful about that and incredibly thorough. It takes 3 years to write a 1,000-page book, and we get 30,000 review comments, and we number and log and respond to each of them. And it's an open, transparent, high-integrity process that hundreds of scientists participate in. And when we don't know something, we say so. And I'll give you a couple of examples of that as we go along. And then, in the end, the IPCC doesn't take a policy position. The IPCC doesn't say to the United States, you should have overwhelmingly nuclear electricity like France, for example. That's a policy question, not a science question. But the IPCC tries to put the findings of climate science in context and in a way that's useful, not just to policymakers, but ultimately to the media, governments, corporations, and the public. So I do think that climate scientists are planetary physicians. I think that there are several things that have caused this issue to come to the fore. And particularly in the United States, I think one of them, probably true globally too, was the view of the Earth from space. Everybody has seen pictures like this, either made by astronauts or by robotic cameras on spacecraft. And children today, the people who are the age of the students at UCSD and Scripps, have grown up with these images. I remember how striking they were when they first started to happen in the 1960s. And an image like this makes a tremendous emotional statement. It tells you right away that the Earth is a unified system. You can see the clouds and the land and the ocean. It tells you how beautiful it is. You see the effects of human activity. You see how thin the atmosphere was, how interconnected everything is, and how fragile in the end everything is. It's a perspective that we knew about in an abstract way, but these photographs have made it concrete. I think the IPCC itself, if I use it as a stand-in for the findings of modern climate science, is part of the reason why we take this so seriously. The IPCC has been in business for 20 years. It's written 4 major reports in 1990, 95, 2001, 2007. It's written a bunch of minor reports. The reports have been examined by the usual suspects, national academies of science in this country and abroad, the governments, professional societies of scientists, and they've been vetted. These are the gold standard. They represent mainstream climate science. Here at Scripps, we use them as textbooks for our graduate students. And if you look at the progression of the statements of the 4 reports over 20 years, IPCC is a little tiny UN agency, by the way. It has no money, has a skeleton staff, office in Geneva. It just organizes scientists to write these reports. The first one in 1990, before the Earth Summit in Rio, simply said this is a serious issue, it bears watching. But by 1995, you see this lawyerly language. It's been negotiated. The balance of evidence suggests a discernible human influence. But by 2001, the third of the 4 reports, you see this statement that there is new and stronger evidence. These statements are negotiated by governments and approved unanimously word by word. It's a 1-sentence summary of a 20-page digest of a 1,000-page report. You know, for the media can't read longer things than this. I'm very impressed with the IPCC. It's not perfect, but it has done a remarkable job, and it's unique. There's no parallel organization in any other field where science impinges on public policy. And I think another factor, especially for people in the United States, was Katrina. Katrina is shown here on a map of the ocean that's color-coded as to temperature. The reds and oranges are the warmest parts. And you know, hurricanes are heat engines. They get their energy from the warm tropical ocean. They only occur in the tropics. They only occur at the warmest time of year. There's a threshold temperature around 80 degrees below which hurricanes tend not to form. And there's theoretical grounds for thinking that in the future, one of the consequences of a warmer world is that the warmer ocean will give rise to more intense, strong hurricanes. You can't say that Katrina or any other hurricane was caused in a deterministic sense by global warming, but you can say that the odds have been changed to favor it. You have to think in Las Vegas terms often when you think about climate. And so it's more likely that a strong hurricane will happen in a warmer world. The heat wave that killed tens of thousands of people in Europe in 2003 was a once on the record, never unprecedented in the instrumental record before. And the research after it has shown that it's unlikely that it would have happened. Not impossible, but much less likely absent global warming. So these natural phenomena, disasters like Katrina and the heat wave, I think have also helped to raise the consciousness of the world. I want to quote you a famous scientist Sherry Rowland here on the subject of whether scientists should advocate policy. The IPCC cannot. It's mandated to be policy neutral, not to be prescriptive of policy. But an individual scientist, so long as he points out that he's speaking as an individual, not on behalf of the IPCC or Scripps or UCSD, can advocate policy. And I think it's important. And one of my heroes in this issue is Sherry Rowland, quoted here, who was then, is still today, a professor at UC Irvine, shared the Nobel Prize in Chemistry in 1995 for his work on ozone. But this quote from the middle 1980s was a quote of frustration. Rowland was very active trying to persuade the United States and other countries to halt the manufacture of chlorofluorocarbons, the artificial chemicals like Freon that cause the ozone hole. The scientists had shown that they're responsible for, and the governments were arguing, and the chemical industry that was making them was arguing about what should be done about it. And Rowland made this statement to a journalist at that time saying, what's the use of having a science that makes useful predictions if you just stand around and wait for them to come true? And I've asked him whether he feels the same way about the climate change, the global warming issue, much more complicated, but very frustrating also for many of us. And he assured me that he thinks it's an exact parallel, and so that I think Rowland is a role model for scientists who want to be active in policy. This is a very old subject. You know, this was not invented recently. It didn't just happen with Al Gore's book or something like that, or movie. This subject goes back to the mid-19th century. And in fact, this is an extraordinary picture here. Let me tell you a bit about the man in the portrait on your left. That's Svante Arrhenius. He also won a Nobel Prize in chemistry, but he flourished in the 19th and early 20th century. His grandson, Gustav Arrhenius, has been on the Scripps faculty for many years, incidentally, but Svante Arrhenius worked in Sweden, and he did the first serious calculation of how much the climate should warm if you increased carbon dioxide in the atmosphere by a certain amount. You know, we use carbon dioxide as a surrogate for a whole suite of gases that add to the natural greenhouse effect. They act like a blanket. They trap the heat that the Earth emits as infrared energy, and they keep the planet warmer than it would otherwise be. They add to the natural greenhouse effect, which keeps the planet habitable. And Arrhenius, who was from Sweden, was interested in what causes ice ages. They didn't know at the time what caused ice ages in the late 19th century. We know now today, by the way. They're caused by changes in the orbit of the Earth around the sun. But Arrhenius was looking into a popular notion that perhaps the amount of carbon dioxide changes in the atmosphere for various reasons, and more carbon dioxide might warm the world and bring it out of an ice age, less might plunge it into an ice age. And Arrhenius was no slouch. As I said, he won a Nobel Prize. He worked on this doggedly for years and came up with an estimate that's within a factor of 2 of the modern estimates of how much climate should warm. If you double the atmosphere's concentration or amount of carbon dioxide, you'll raise the temperature by something like 5 degrees Fahrenheit. And Arrhenius was within a factor of 2. He thought it was a little bit more than that. This was pre-satellite, pre-supercomputer, pre-quantum mechanics. You know, quantum mechanics is the part of physics that explains why these gases add to the greenhouse effect. But Arrhenius knew about this in the 19th century and published it. And laboratory scientists were putting tubes of carbon dioxide in laboratories and shining infrared beams on them and measuring the absorption. This is stuff that was well understood in terms of the available science of that day. The person on the right, the live person in front of the portrait, is Bert Bolin, the first chair of the IPCC, a scientist of immense vision and originality and personal integrity who helped to form the IPCC in the 1980s when it became clear that some such organization was needed by policymakers so they could understand the science and have it presented to them in a believable way. Bolin, who died, by the way, not quite a year ago, he died late December of last year. He was too ill to go to the Nobel ceremony on December 10th, but he knew about it and he was thrilled by it. And as we all were, the recognition to the IPCC was completely unexpected. Gore had been tapped, but IPCC was a surprise. And Gore and many others at the ceremony and since paid homage to Bolin's role. And I'm going to say a bit more about Bolin later on. In the nature of advocacy, I'll come back to the science shortly, but let me show you something in the nature of advocacy. Every year, the United Nations climate negotiators get together to try to agree what should be done. So for example, the Kyoto Protocol came out of one of these meetings. There's one going on now in Poland. The one before that was a year ago in Bali, and a group of scientists, of whom I'm one, organized a publicity action, you might say. We wrote a declaration. We had about 200 good climate scientists from 20 or so countries around the world sign it. We held a press conference in Bali, and here's what it said. I won't read it to you, but the point is quite tricky here. The third passage here says, we advocate a goal of limiting warming to a particular level, 3.6 degrees Fahrenheit, above what it was in the 19th century. You see, if you look back to the middle of the 19th century, there was no strong human influence on global climate. It's only once mankind started using fossil fuels, coal, oil, natural gas, that give off carbon dioxide, which began in the 19th century in significant amounts and is accelerated enormously in the 20th century. It's only when mankind does that that the climate begins to warm, the greenhouse begins to be stronger. And so we took, and this is not a science statement, we took as a, you might say, a value judgment that the 200 of us could agree on, that 3.6 degrees Fahrenheit above the 19th century temperature ought to be a reasonable limit for avoiding the likelihood of dangerous human-caused climate change. You see, that's a statement that science can't do for you. That depends on a lot of things, on your personal values, on your tolerance for risk, for example, or on the credibility that you give to the science, or on what you think you can do to adapt to the consequences of a changing climate. Lots of things bear on that. It's only once you've said, there's some number that I'll take as my target. And as you see here, the last line says the European Union, a very big place with more people than the United States, has agreed formally on this 2 degrees Celsius or 3.6 Fahrenheit as a target. Then science comes to your aid. It's as though you decide yourself what weight you want to have. Then the whole business of nutrition and so on helps you decide what you have to do to get to and maintain that weight. So we accepted the European Union recommendation, and then we tried to say as succinctly as we could for the delegates in Bali what the science tells you about that. And here's what we wrote. It's consistent with the IPCC report. It says you have to reduce the rate at which we emit greenhouse gases. Carbon dioxide is the most important one, but it's roughly 2/3 of the problem, and there's another third made up of methane, nitrous oxide, many other gases. You have to reduce the rate at which we're emitting that by at least 50% below 1990 levels. Mind you, today we're substantially above 1990 levels. Every year, the rate at which the world emits greenhouse gases goes up, not down. And then you have to stabilize the amount. That's the concentration is jargon for amount. The amount of gases in the atmosphere below a certain level, 450 parts per million. That means if all the gases were carbon dioxide, you took 1 million molecules of air, 450 or fewer of them would be carbon dioxide. We actually, it says carbon dioxide equivalent because we can convert, you might say, the heating role of the other gases to CO2, so we can speak just of CO2. And to do that, to keep the emissions below this level, so that the amount of the gases gets below that level, then the science tells you you have to quickly peak the emissions. You get to a point where you can no longer increase them year on year, and then have them start to decline globally. Mind you, these gases stay in the atmosphere a long time, carbon dioxide well over a century, and so the result of all the emissions of all the people in the world and their ancestors is what's in the atmosphere now. So you can't change the San Diego climate by changing San Diego's emissions. You can only change the global climate by what the whole world does. That's the reason for the urgency. That's why you can't sit around and procrastinate and talk about it for a long time, because there comes a point beyond which you can no longer achieve that target. If your target was somewhat looser than 3.6 Fahrenheit, you get to have more emissions going longer time. But whatever global warming number you pick as your target, and these are the numbers for the European Union's pick and our pick, you get a set of numbers like this. It's considered very bad taste to give a talk on this subject at Scripps without showing this graph, the most famous graph in earth science. This is Dave Keeling's record of the amount of carbon dioxide in the atmosphere. Keeling argued correctly with Rowland that if he measured it at one pristine place, and he picked Mauna Loa in the middle of the Pacific Ocean, that would be representative of the whole world. Keeling invented the instrument and saw through to the measurements up until his death 3 years ago, and the work is now being carried on by others, including his son, who's a member of our faculty. But here you see the inexorable rise of carbon dioxide. It's entirely due to human causes. We can tell by clever detective work, in particular showing that the isotopic signature of carbon from fossil fuels is different from carbon from, say, volcanoes, that this rise in the atmosphere from around 315 on annual average when Keeling's measurements began half a century ago to up in the 380s today is entirely human caused. We know a great deal about this, again, due in large measure to Keeling's own work. We know that fossil fuels are responsible for most of the rise. Deforestation is a secondary cause. We know what causes the annual wiggles. Those are photosynthesis and respiration, trees taking in CO2 from the atmosphere in the spring in the northern hemisphere, giving it back by respiration in the fall. So we know a great deal about this. Arrhenius didn't know this, by the way. Arrhenius thought it would take 3,000 years to double carbon dioxide. He was wrong by about a factor of 20. He did not foresee the rapid rise of population in the 20th century and the increasingly strong reliance on fossil fuels. Today, 80% of the world's energy in round numbers comes from coal and oil and natural gas. This is not an IPCC report. This is my own way of thinking about this. I think, although I think many IPCC scientists and others would agree, but this is simply my personal view here, I think that the uncertainty that will always be there in any kind of science, as I've said, ought not to be an excuse to prevent action. Making decisions under uncertainty is part of life. And medical science is a clear analogy. And I think many of the things, this is the second point, that you'd want to do, like conserving energy and replacing energy inefficient appliances and vehicles and so on with energy efficient ones, are good for the climate, but also have other benefits. If your car suddenly got twice as many miles per gallon tomorrow as it did yesterday, because you've traded it in for an otherwise identical car, think of all the other things you do besides helping the climate. You put money in your pocket, you reduce the dependence on foreign oil, you reduce air pollution in your town, and so on. The third, I actually have a quote from Bill Buckley in mind. He was not a liberal Democrat, but he said at some point, you know, I'd rather be governed by the first 500 names in the Boston phone book than by the Harvard faculty. And I think he had a point there. But if you are trying to make a decision on an issue on which the Harvard faculty has expertise, you ought to hear them out before you make your decision, or your elected representative does. And I think the ozone issue, in which we made the right decision, we passed the Montreal Protocol and subsequent stronger agreements and phased out the manufacture of the offending chemicals, and the ozone layer is on track to heal, although it may take several decades to do that. The fourth point is straight from the medical canon, of course. And I'm going to talk about unintended consequences in a short bit when I talk about geoengineering, the proposals floating around to try to make intentional changes to the climate system in a way that would counteract the inadvertent ones that we've already made. This cartoon is from the IPCC report, and it shows something that's not widely appreciated, although here at Scripps we know all about it because we've been part of it. The science of climate change has increased in its realism and sophistication and comprehensiveness during the same recent decades that the climate has been changing, so that it's unrecognizable from what it was. This year is not only the 50th anniversary of Dave Keeling's first measurements, it's my 50th anniversary in this field. I went off to college 50 years ago as a freshman to study meteorology, and that was long before this graph even starts. You can see in the upper left the best computer models we had in the 1970s. There were none when I was in college. Were simple computer models with a simple water cycle. By the 1980s on the upper right, we'd added a few more features: clouds, a rudimentary land surface, prescribed ice and snow. Then the next 4 panels are labeled FAR and SAR and TAR and AR4. That's IPCC jargon. FAR is the first assessment report, the one that came out in the 1990s. SAR, the second in 95, TAR, the third in 2001. They couldn't use FAR again for the fourth one, so they called it AR4. And you can see that in those reports covering the last 20 years, essentially, the availability of these computer simulations, our best way to put the world in a test tube, so to speak, and experiment on the virtual Earth in ways that we cannot on the real Earth, the models have increased almost month after month in comprehensiveness and sophistication. So if you look at AR4 at the bottom right, the current models, they include not only a realistic simulation of the atmosphere and the ice and snow and the land surface and the ocean with its circulation and so on, but also of chemistry and of interactions between the system, the exchange of carbon dioxide and other gases, for example, between the atmosphere and the ocean and the world of plants. At the same time, computers have gotten faster. And that's illustrated here. The top picture, the FAR, 20 years ago, we had divided the world into blocks, about 500 kilometers or 300 miles across. And if you look carefully, that's Europe in the lower right on the top picture there. And you see the 2 blocks for the Alps and maybe 6 or 7 for the whole Mediterranean. There wasn't much detail. That's because computers were slow 20 years ago. So we've profited from the enormous increase in computer speed and the decrease in cost. Moore's law is the jargon phrase for it. Computers have got faster, and we climate modelers are customers for the fastest computers. And so you see through this evolution of these 4 IPCC reports, the bottom one, AR4, current models have grid sizes that are about 5 times smaller, so we get much more accurate solutions to our equations, we can represent much finer detail, and we can begin to deal with local climate phenomena and not just with large-scale averages. I've learned through going to conferences like the one at Bali, I've been to several, and there's a very important one coming up in a year in Copenhagen, and I'll be there, that the arguments are often not, among the delegates trying to see their way through to an agreeable policy, often not scientific. And instead, considerations of equity and justice and fairness dominate. And there's a major gulf in this now, and it's going on in the negotiations currently on in Poland, about north-south equity. What ought to be what the treaties call differentiated rights and responsibilities between the developed, wealthy world and the developing, not yet wealthy world. And there's a great deal of finger-pointing. China recently passed the United States as the country that emits more carbon dioxide than any other single country, because although its per capita emissions are smaller than ours, it has many more people than we do. And so you can imagine the finger pointing. The United States points a finger at China, so to speak, metaphorically and very diplomatically, and says, you are responsible for the continued rapid growth. We've pretty much stabilized. And China points to the United States and says, who are you, having gotten rich and prospered by the availability and exploitation of cheap, readily available coal and oil and gas, to tell us, whose people want what you would consider basic necessities, electricity, for example, that we can't have it because of a problem that you, the rich West, have caused. And it's not easy to find solutions to that kind of issue. And there are many, many, many of them now. Poland, for example, makes its electricity largely from coal, which is a dirty fuel, more global warming per unit of energy than oil or natural gas. And so it objects to, say, a country like France, whose electricity is 80% nuclear, suggesting that Poland can cut way back. There's a strong flavor of intergenerational equity. As I said, it's like quitting smoking. You are doing things for the benefit of the next generation and the one after that. And people have different opinions about that principle. Geoengineering is tempting. You can think of ways in which, for example, you can make the planet more reflective. You can put small particles in the atmosphere or their chemical precursors up into the atmosphere, a kind of artificial volcanic eruption, because volcanoes, you see, big volcanoes cool the world for a year or two, by a degree or two, typically. So you could do that on a continuing basis, you meaning all of humanity. But what do you do about side effects? What do you do about unanticipated consequences? What do you do about having put it there, you have to keep on putting there. It's addictive. What do you do about winners and losers? Who has the ethical or legal or moral right to prescribe doing that for the whole world? Furthermore, if you did it and it worked perfectly and everybody loved it, it doesn't solve the whole problem. For example, the oceans are becoming more acidic because the carbon dioxide that we put into the atmosphere largely ends up in the ocean ultimately, which from a chemist's point of view is dilute carbonic acid becoming less dilute. So the ocean's getting more acidic. And that has potentially profound consequences for marine life. For example, small animals that form calcium carbonate shells are less able to do so in an acidic ocean. This isn't simple. And it's very unlikely, because those particles that reflect sunlight are not little negative CO2 molecules. You're trying to compensate for something you're doing to the infrared side of the energy budget with something on the sunlight side of it. And it's very unlikely this can be done, but it's tempting. It's as though, to make a gruesome medical analogy, it's as though you drank too much wine every night, but rather than cut back, you asked for a pill that would save your liver and those ugly blotches on your face and the fact that you fell over during talks. I think it's very tempting, geoengineering, and I'll give you my prescription for it later on. I promised our organizers not to overwhelm you with scientific detail. It's a 1,000-page report we produced with lots of graphs. And here's an interesting one. I thought I would show you this one here because it's striking. Okay, you see 6 panels here. These are the 6 inhabited continents: North and South America, Europe and Africa, Asia and Australia. This is the whole world average together. This is all the land surfaces of the world, and this is all the ocean of the world. And in each of these 9 pictures, the black line, let's look at this one here, is the average temperature measured from early in the 20th century up until today. So this is 1900 on the left, 1950 in the middle, 2000 on the right, roughly speaking. And you can see the temperature in all 6 continents and the world and the ocean has gone up. The black line, especially in recent decades, say from about 1970s through the early part of the current century, has been a rapid rise. That already tells you a lot. For example, the fact that it's warming over the ocean tells you this is not a side effect of temperature measurements in cities. It's not an urban heat island. But it's true everywhere. It's ubiquitous. Not exactly the same graph, but you see this warming in recent decades everywhere. The blue and the pink are the result of trying to simulate that with these computer models that I spoke about earlier. And the difference between the blue and the pink is that on the blue lines, the computer's been told not to take into account this change in greenhouse gases, but just natural things like the changes in the sun or changes in volcanoes. And in all 9 cases, the blue simulations based just on natural input to the computer models don't reproduce the observed warming. And the pink ones that include the increase in greenhouse gases and in small particles do. That's part of one line of evidence for the IPCC's statement that the change we're looking at is largely human-caused. The IPCC summarized its findings in 2 statements. Here's one of them. Warming of the climate system is unequivocal, and there are many lines of evidence that lead to that statement. There's not one that hangs from some slender thread of evidence, but many, many lines of evidence. And 2, most of the observed warming in the last 50 years or so is 9 chances out of 10, that's the calibrated very likely statement there, due to the observed increase in anthropogenic, meaning human-caused, greenhouse gas amounts. So the warming is unequivocal, and it's nearly certainly human-caused. You can read the whole IPCC reports and the summaries that I've been quoting from. They're available on this IPCC website. And there are many, many, you might say, paraphrases and digests of them. This is another graph that I didn't want to leave out tonight. In each of these 3 panels here, you see the change from 10,000 years ago on the left to the present today in the amount of carbon dioxide in the atmosphere, that's this here, methane, that's basically pure natural gas and other greenhouse gas, and nitrous oxide, which rises largely due to agricultural practices. The insets here are an exaggeration of the last century and a half or so. But stick to carbon dioxide. What you can see is that for nearly all of 10,000 years, up until, in fact, the 19th century, carbon dioxide oscillated slowly about a value that's in these units, same as Keeling's, 280 molecules per million molecules. It's now shot up to above 380. This is the Keeling curve here, grafted onto the earlier data, which comes from ice cores. We know this because we've analyzed air trapped in ice in Greenland and Antarctica. That's the only way we know what the chemical composition of the atmosphere was centuries ago. There was no Keeling and no instrument 10,000 years ago. So today it's true that better than 1 out of 4 molecules of carbon dioxide in the atmosphere is there because of human causes. That's as close to a fact as scientists will ever give you. We just know that. And it's true for the other gases too. So we've taken control of important aspects, inadvertently, of the chemical composition of the atmosphere. I'm not going to read this to you, but I'm going to let you skim it to see some of the observational evidence that we have here. The Earth is substantially warmer than when instrumental records begin. There is a statistically significant increase in hurricanes in the North Atlantic. It's tricky. It's an area where there's a lot of research still going on. It's one of the things where IPCC leveled and said there are questions we don't know. Hurricanes are rare. It takes a long time to build up robust statistics. The Arctic is warming more rapidly than elsewhere. That's because as the Arctic warms, snow and ice melt, the darker surface absorbs more sunlight and adds to the warming. And the last one is interesting, and it's partly a Scripps result. Most of the warming, 80% and a little more actually of the amount of heat added to the system is in the ocean, which are warming not all the oceans, not just in the surface layers, but to depths of 2 miles. As I said, a lot of Scripps contribution to that result. I like this picture. It shows the human effect very clearly, and I'm asking you to imagine what will happen later in this century when some of the parts of the world that don't have heavy use of electricity and other man-made energy join the fossil fuel club. We're trying to look ahead. IPCC doesn't make forecasts, but it examines a number of hypothetical scenarios, and it's concluded that sea level, which is increasing because in a warming world sea level rises, the ocean expands, and also water gets added to the ocean by melting ice on land. It will expand up to 2 feet. And the second paragraph is one of those statements about the honest physician telling you there's things we don't know, but you better be on the lookout because they're potentially serious. And that is, it's possible, and it happened in the past when this kind of warming was sustained for a long time. We don't know whether it can happen on a timescale shorter than centuries or millennia, that ice sheets can destabilize in both Greenland and Antarctica and lead to a much stronger sea level rise. The climate system is not a simple linear thing. It's often acts like a light switch rather than a dial. You know, old-fashioned spring-loaded light switch. You push and push, nothing happens until you push a little hair more, and then it flips over to the other position. The climate system has instabilities like that, or thresholds, or tipping points, and by their very nature, they're unpredictable in detail. You can't tell exactly when the light switch will push. All you can say is that as the planet gets warmer, it's more likely than before it had warmed that you'll trip one of these little triggers. That's the risk tolerance, part of the argument that I mentioned earlier. This is the other IPCC figure that I felt I had to show you. The graphs over here show the last 10 years of the current century in scenarios of relatively modest emissions of greenhouse gases, more and still more. These are lighter, heavier, and heaviest dependence on fossil fuels, you might say. This is the same thing for the decade of the 2020s, not so far away. The darker the red, the greater the warming, and you can see that there's not much difference in the 2020s. It takes time for the cumulative effect of using more and more greenhouse gases to show up. But in the 2090s, when some of your children and their children will surely be here, then you see a very different planet. Here, the seasonal sea ice in the Arctic is gone. All the continents are much warmer. For you scientists in the audience, this is the same thing expressed probabilistically in the 2020s here and the 2090s here. You see these fat tails. That's because these are means, these are averages, whereas there's a chance that these will be under forecasts. I'll say a word about the IPCC. I'm getting near my finishing point here, but I wanted to tell you a word about how it was put together. This 1,000-page report on the physical climate system, there are others on adaptation and mitigation of climate, was written by 150 people, and we were chosen by IPCC for disciplinary excellence and knowledgeability, but also for various diversity criteria, which you can see here. There were a quarter of us were young in the sense of being 10 years or less past PhD when appointed. 3/4, including me, had no stake in the earlier reports, so we were coming fresh to it. And 35% of the authors in our report were not from the first world, not from the countries that generally have the supercomputers and satellites, but I can tell you through having worked with these people that they brought a very valuable perspective. We wrote 3 separate drafts of this 1,000-page report and saw it through, and as I said, responded to 30,000 review comments. It was a memorable experience, and I'm very glad I did it, and I will never do it again. I wanted to show you what was happening now. This is temperature from the 1970s to the present, and this is the blue and the red thin lines here are one set of data compiled by 2 research centers. You see there's a lot of variation year to year. These are the annual averages. The blue and the red smooth heavy lines here are the annual smooth ones. So the world is still warming. If your skeptical neighbor says global warming stopped in 1998 and points to this point here, point out to him that this was an El Nino year, and El Ninos are responsible for these peaks, La Ninas for the troughs, and if you do the smoothing, which is the right way to look at the long-term trend, you're back on the track here. Then the dashed lines here were IPCC projections from earlier IPCC reports. And a number of us wrote a paper examining these kinds of trends for temperature, for carbon dioxide, for sea level, and concluded that the previous IPCC reports hadn't exaggerated the danger. I'm going to close with some remarks here. The climate system is very much a global commons. And I think that advocates of geoengineering, and there are many ways you could think of tinkering with the planet, ought to take the ethical implications seriously. And my personal prescription, one person's view, is that it's like nuclear war. Study it, do research on it. And in the case of geoengineering, do small-scale tests, do laboratory experiments, do computer simulations, learn all you can about it, and refrain from trying it. If it's the last resort in a worst-case scenario, do everything you can to avoid that scenario. I wanted to say a word about Dave Keeling, whom I knew for the last 25 years or so of his life, an extraordinary person, legendarily persistent in making these observations. This is the observatory on Mauna Loa where his instrument was. It's still there. It's retired now. It's a museum piece, but it chugged away for decades. This is the first few cycles of the Keeling curve. At about this point, Keeling had already been through several struggles with funding agencies who said, we don't want to do routine monitoring anymore. But fortunately, he persisted. And today, if you go to the Great Hall of the National Academy of Sciences in Washington, together with the double helix of DNA and Mendel's P's and Darwin's finches, you will see the Keeling curve. So Dave is widely recognized now for being the great scientist that he was. And I think finally, I wanted to leave you with the thought that considerations like ethics and equity and justice and fairness are not just abstractions. And in fact, if you look to successful environmental agreements in the past, like the phase-out of the ozone-depleting chemicals, they were very much in play in reaching the Montreal Protocol and subsequent agreements to end the manufacture, so that, for example, technology transfer from the rich countries to the less rich countries happened, and funding was transferred as well. The US had invented chlorofluorocarbons, freons, in the 1930s, and it invented, DuPont and others, invented the ozone-safe substitutes for them and made them widely available. And I think today we're facing a much harder problem because freons are a specialized gas of limited use, whereas today the global warming issue is due primarily to the fact that humanity depends so strongly on fossil fuels for its primary energy supply, and they permeate every aspect of our lives. So it won't be simple, and there won't be a magical bullet, and all the suggestions that have been made deserve exploration, and people will not find a single magical substitute for oil and coal and gas. Instead, we're going to be looking at renewables and nuclear power and carbon sequestration and storage, And it's certainly at all the low-hanging fruit, the cheap or free or negative costing efficiency and conservation improvements. I'm going to leave you with the final thought now, which is that there's a need to communicate science in this issue that is paramount, because political action will happen when political will is mustered and when politicians feel that voters take this seriously. And yet we live in a country in which scientists don't generally communicate well. Some of them should never be allowed near a reporter. In which society, I'll give you one scary number from the NSF poll, half of Americans don't know the Earth goes around the sun once every year. And we're trying to explain some pretty complicated physics and chemistry to them. Furthermore, there is a disinformation campaign exactly similar to that mounted by the tobacco industry against the smoking and health connection some years ago. And in the US especially, this issue has become partisan. If you tell me how somebody voted in 2000, I'll tell you what they think about an inconvenient truth. The message and the messenger get confused. And often I think people's policy positions get expressed as views about science. So that instead of saying something about what's wrong with climate models in terms of their physics and chemistry, people say, I'm not in favor of government interference with free markets or with ceding national sovereignty to international agreements, or taxes on carbon and so on. That's fine, but I think we can keep the science and the policy separate, and we should. There's no such thing as Republican or Democratic cloud physics or liberal or conservative ocean circulation theory, and I think we can talk about the science and the policy separately. The media is something else. Maybe we'll have questions about the media. My view on the IPCC report is it's wonderful science assessment, but it still needs to be communicated. And my metaphor for it is that it's like ore that has to be brought to the surface and machined into books and television specials and movies and classroom materials and so on. Thank you again for looking at my book, those of you who have. Thanks again. Would the recession have a positive or negative or neutral effect? You know, I don't know. And it's one of the great things about getting interested in this subject. You know, my degrees are in meteorology, but people are happy to ask me questions about economics and public policy, which I'm totally unqualified. But, I mean, if you listen to the statements that, in fact, during the campaign came from both sides, both McCain and Obama took climate change very seriously. And McCain in the Senate, for example, was a leader in pushing legislation that would have limited emissions. Obama has said that green energy and reduction of fossil fuel use is going to be part of his way of getting out of the recession, that he's going to invest in those areas. And I think there's an enormous challenge and an opportunity there. So I don't think the recession has to be necessarily something that sucks away all the energy, you might say, or all the political will, so that we put this on the back burner. I think that many things you'd like to do for the climate are also good for the economy. And by the way, business is not monolithic on this issue here. After all, Toyota is selling all the Priuses it can. And the reinsurance industry is worried about more Katrinas. You know, there's plenty of business interest in this topic and plenty of will on the part of large corporations. Multinational corporations have to obey their Kyoto commitments, even in the US, which didn't sign Kyoto. So there's a great deal that I think can be done. It's a question of whether the political will be mustered to do it. There's exciting things going on in other countries. In the US, I find personally that a great many interesting, encouraging developments at the state and local level. I'm a fan of AB 32, the law that's passed and signed by the governor in California, that will reduce emissions by mid-century by a very large amount, and that has teeth in it, has penalties up to and including criminal penalties for failure to comply. We'll see how that's implemented. Right now, the foot dragging, the lagging, in my view, has been largely at the federal level, and the progress has been at the state, local, corporate level. So I think a great deal can be done, and I hope will be done. I'm optimistic on Tuesdays, Thursdays, and Saturdays. Yes? Okay, the question was about the numbers that I showed you in the Bali Declaration, suggesting that to keep the temperature the maximum warming within 3.6 degrees Fahrenheit above the pre-industrial 19th century level. The carbon dioxide should be kept at the level of 450 parts per million, or CO2 equivalent should be at that. And more recent research suggests that a smaller number might be needed. I think the recent research is probably right, and that it may be very hard to do 3.6 degrees. There's a lot of recent research, again, some of it done here at Scripps, suggesting that there's more global warming that we're already committed to that's in the pipeline because it's temporarily masked by air pollution. That is to say, we've got particles in the atmosphere that, in essence, have prevented us from seeing all the warming that's coming out. And as those particles are cleaned up by, you might say, global efforts like the Clean Air Act in the US, we will see greater warming. There's also interesting questions about the biogeochemistry of the gases involved. It's quite complex, but it may be harder than we thought, and so the numbers that I gave you may have to be revised. The price you pay for the thoroughness, the peer review, the transparency, and the integrity of the IPCC is they're always a little bit behind the time. And so the research that's summarized in the 2007 report was published no later than roughly mid-2006, and therefore was completed, say, a year before that, at the latest. And therefore, this is a rapidly moving field, as I've tried to convey to you. We're learning more all the time. And so there's recent research out suggesting what I've just said and what you alluded to, but it hasn't yet, you might say, stood the test of time. It hasn't been through the fire of science where other scientists will look at the results, replicate them, critique them, and so on. That's already going on. But indeed, it doesn't seem likely that it's going to be easier than we thought to keep it to that level.
I run a tight ship here, but thank you very much, Richard. That was a wonderful presentation.
Okay, thanks again.